Hello everybody, welcome back to the Gregorious Maths video. Today is the first video in the Lenten Mathematics series, where I will be doing one video a day, but unlike the Advent calendar, I will be doing more first year undergraduate mathematics stuff because I'm sort of making these videos for myself to force myself to learn the bookwork for my exams in the summer. So yeah, full disclosure, that's what this is. Hopefully something along the way is still I'll still try and make it interesting, but you know, that's full disclosure, that's what I'm doing. And yeah, it will end as last time with the notebooks video. And yeah, apologies to those who are looking forward to tackling topoi. I'll have to do that after the summer. Yeah, I should never have made that introduction video, but oh well, we move. Okay, so how am I going to kick off this series? Well, I'm going to kick it off with a proof of inclusion-exclusion, and we're going to do it probabilistically. So in order to motivate this, let's just take a look at a pattern first of all. First things first, the probability of A union B. This is a well-known result. We can write A union B as the union of two disjoint sets as P of A union B set minus A intersection B. Now these two things are disjoint, and this is still equal to that. And this is now given by P of A plus the probability of that, which is just P of B minus P of A intersect B, like so. Okay, this is well known. Fine, whatever. Now, let's apply this to three sets. So what about the probability of A union B union C? What happens now? Well, let's apply this formula first. So this is the probability of A union B plus the probability of C minus the probability of A union B intersect with C. This is equal to, let's expand this guy out now. This is the probability of A plus the probability of B, and then plus the probability of C, minus the probability of A intersect B, and then we still minus the probability of A union B intersect C, but we can just write this as A intersect C union B intersect C, right? Because it's going to be the stuff that's in both. Yeah. Because this is the stuff that's in both A and B and C. So it's in either A or B, and it's in C. And this is just the stuff that's in A and C, union with the stuff that's in B and C. So if you just stare at this long enough, you can probably convince yourself that this works. And if we now expand this, this is the P of A plus P of B plus P of C minus P of A intersect B minus, and then we just apply this formula again. So we get P of A intersect C minus P of B intersect C plus P of A intersect B intersect C, like so. All right, so what's the pattern here? What can we see is happening? Well, for two sets, we just had P of A plus P of B, and then we took away we had all the singletons, and then we took away the intersection. Here we still have all the singletons. Then we take out all of the pairwise intersections, and then we add the triple intersection. So in general, it looks like if we have n sets, we add the probabilities of all of the sets, like A1, A2, up to AN, and then we subtract all of the pairwise intersections, and then we add all of the triple intersections, and then so on, alternating. So, first things first, that's all well and good, but actually writing this out is a little bit technical. So let's write this down in a statement that we can actually prove. So theorem, the probability of the union from I equals 1 to n of ai is just given by the sum from k equals 1 to n of minus 1 to the k plus 1. So this is the alternating signs. And then we sum over all of the intersections. So how do we denote this? Well, over all I1 less than up until ik less than, but where all of these indices are between 1 and n, of the probability of ai1 intersect up until aik, like so. So these are this sum here sums over all of the intersections with k different subsets. And we sum from k equals 1 to n, so we get all of the different amounts of intersections. And the sign here corresponds to the sign that we see there. All right, so how do we prove this? Well, we'll prove it inductively, starting with n equals 2, which we have right here. So let's assume that this is true for n minus 1, okay? So in that case, the probability of the union from I equals 1 to, let me write proof. I equals 1 to n of ai is equal to the probability of the union from I equals 1 to n minus 1 of ai union an, like so. Now this, by the case n equals 2, is given by the probability of the union from I equals 1 to n minus 1 of ai plus the probability of an minus the probability of the union from I equals 1 to n minus 1 of ai intersect an, like so. Okay, now what we're going to do, just for convenience, is we're going to let this thing right here equal to bi. So bi is just the event ai intersect an. And then we're going to apply the induction hypothesis to get that this is equal to the sum from k equals 1 to n minus 1 of minus 1 to the k plus 1, sum over all I1 up until ik, which are all between 1 and n minus 1, of the probability of these intersections. And then we subtract this. So, okay, just remember that this is bi. So let's just put the sign here. So we add the sum from k equals 1 to n minus 1 of minus 1 to the k, sum over all of all the bi's. But the intersection of all the bi's is just going to be given by ai1 intersect up until aik, and then we just intersect this with an, right? And then don't forget about this final piece, which is the probability of an, the singleton. Now, okay, how has this actually done anything? Well, let's look at what we have here. Firstly, here we have all of the intersections that have no an. So we get all of the singletons, all of the double, everything that doesn't have an an, we get from here, and the sign is correct. In here, we get everything that has an with the sign adjusted because the extra an is going to flip the sign, except for the singleton, because this, if you notice this sum, since we're starting from k equals 1, we're always going to get at least one intersection in here. So we get everything with the sign adjusted correctly, which contains an. And here we get everything that doesn't have an in the intersection. But now we just get the extra singleton from here. So we're done. This is actually completely, and let's just write out the formula. This is equal to the sum from k equals 1 to n of minus 1 to the k plus 1 sum over all over all the indices I1 up until ik between 1 and n of ai1 intersect up until aik, like so. And that's done. We're done. Okay, great. Now, that's proven very nicely, I think. It's quite a satisfactory proof in my opinion. And just to top this all off, you may be familiar with the following version of inclusion-exclusion, which doesn't talk about probabilities, but it talks about the size of the sets. Whoopsie daisy. So we talk about the size of the set given by A1 union up until, let me write it in nice and neat, of the union from I equals 1 to n of AI is given by, you might see the formula, the sum from, pretty much the same formula, sum from k equals 1 to n minus 1 to the k plus 1 of the sum over all of the I1 up to ik less than or equal to n of the size of all of these intersections, ai1 intersect aik, like so. And well, this is not exactly the same thing as this. So how do we reconcile this? Well, our probabilistic version is actually more general, because what we can just do is we can consider the probability space omega fp, where omega is just some finite set, and p of a is just given by the size of a divided by the size of omega. So a is just some subset of omega, f is the sigma algebra, is just the whole power set, and our probability function is given by p of a is just, the probability of a is just the size of a divided by the size of omega. And if we apply this probability then to our probabilistic version of inclusion-exclusion, then we get that the probability of this is equal to that. So what do we actually get? We get the probability of the union from I equals 1 to n of ai, which is just given by the size of the union from I equals 1 to n of ai divided by the size of omega. This is equal to the sum from k equals 1 to n of minus 1 to the k plus 1 times by the sum over the probabilities but the probabilities are all just given by the size of the intersections, aik, divided by the size of omega. And since we're dealing with sums here, we can just cancel out the sizes of omega and we get back to there. So, and there's plenty of applications of this. So yeah, that's a little probabilistic proof of this statement, I guess. And yeah, hopefully this was somewhat interesting, I don't know. Comment down your favorite application, or like the coolest application of inclusion-exclusion in the comments. I'd love to hear the like wackiest ways you can use this, because there are tons of ways to use this formula. So I'd love to hear your thoughts, and I'll see you hopefully tomorrow. Good day.